Here's example 12 of evaluating trig with inverse trig. So we're going to use this flowchart again like we've been using. And if you want to copy this flowchart to follow along with, check the video description. There's a link in there. You can click that link, open this up, print it out, and follow along if you'd like. Okay, so let's go ahead and get started here. So example 12, inverse cosecant of the secant of 12 pi over 7. Okay. So first of all, is there a domain violation? No, there's not, because secant of 12 pi over 7, that's totally fine. 12 pi over 7 is in the domain of secant. And when we evaluate that, that's going to give us something that's okay to put in the inverse secant function. Okay, just by the way, the domain of the inverse cosecant function. The way the domain of the inverse cosecant function is, if you evaluate the secant function, then you're at a number like this anyway, at a number like that, everything's going to be okay in the inverse cosecant function. So we don't have to worry about being tricked or anything like that there. So is there a domain violation? No. Is the function paired with its own inverse? No, it's not, because it's inverse cosecant paired with secant. So it's not cosecant and inverse cosecant, it's not secant and inverse secant, it's secant with inverse cosecant. So is the function paired with its own inverse? No. Can the problem be solved using the unit circle? In other words, is this a nice number on the unit circle? No, it's not. It looks like it might be because it's a number times pi over another number. But stuff over 7, that's really goofy. That's not a nice number on the unit circle. Not a nice angle. So no. Can the problem be solved using the unit circle? No. Is the inverse function on the inside? No, the inverse function is on the outside. Inverse cosecant on the outside, plain old regular secant on the inside. Is the inverse function on the inside? No, follow the no path. Is the function paired with its own inverse? And again, we asked this before, but we have to ask it again because it does affect what happens next down here. Okay. Is the function paired with its own inverse? No, remember, no, it was not. So no. Is the function paired with the inverse of its cofunction? So we asked this question in the last example, and remember, it sounds like kind of a mouthful, but it's really not that bad. Is the function paired with the inverse of its cofunction? So what we can do is say, okay, what's the function? The function is secant, the inverse is cosecant. So is the function, is secant paired with the inverse of its cofunction? What's the cofunction of secant? It's cosecant. What's the inverse of cosecant? It's inverse cosecant. Okay. Is secant paired with inverse cosecant of x? Or just inverse cosecant? Yes, secant is paired with inverse cosecant. So yes, since secant is paired, so yes. Is secant paired with inverse cosecant? The inverse of its cofunction. Yes, secant is paired with the inverse of its cofunction. Yes. Okay, so secant, its cofunction is cosecant. The inverse of that is inverse cosecant. So yes. Is the function paired with the inverse of its cofunction? Yes, it is. So now we use the complementary angle theorem, and then either cancel or use reference angles after that. Okay. So again, like we mentioned the end of the last video, the complementary angle theorem technically applies to only acute angles, but the result that the complementary angle theorem has is actually true for more general angles. So even though 12 pi over 7 is not really an acute angle, we can still use the complementary angle theorem, even though we probably wouldn't really call it that, but it's just a more general identity that's true, which is nice. So, okay. It's true as long as there are no domain violations, which we don't have to worry about here. So anyway, now why do we want to use that theorem? The reason we want to use it is so that we can convert the secant to a cosecant, and then we'll have cosecant paired with its own inverse, and that'll be easier to work with, and that's nice, that's great. Okay. So anyway, what we want to do is say, okay, secant of x is cosecant of pi over 2 minus x. Okay, and then specifically in this case, our x is 12 pi over 7. So secant of 12 pi over 7 is cosecant of pi over 2 minus 12 pi over 7. Ugh, alright, so now we have to get a common denominator. So Denominator 2, denominator 7, common denominator is 2 times 7, which is 14, so multiply this guy by 7 over 7, multiply this guy by 2 over 2. So then what we get is, let's zoom in a little bit. So what we get is, cosecant of pi over 2 times 7 over 7, that's 7 pi over 14, and then minus 12 pi over 7 times 2 over 2 is 24 pi. 24 pi over 14. Ugh, terrible numbers. And then this equals cosecant of 7 pi over 14 minus 24 pi over 14 is negative 17 pi over 14. That's just awful. All right. Anyway, it's good in a way though, because now that we've just found out that secant of 12 pi over 7 is cosecant of negative 17 pi over 14. So now we can use this fact and put that back into this original problem here. So we'll zoom out just a bit. So inverse cosecant of secant of 12 pi over 7 is inverse cosecant of the cosecant of negative 17 pi over 14. Okay, so we have that going on now. All right, let's see. What's happening next? So what did the flowchart say to do next? Next, the flowchart said to use complementary angle theorem, which we technically did, even though it's not an acute angle. So we use this general fact, like we mentioned in the last video, so keep that in mind. And then either cancel or use reference angles. So can we cancel? So what was the rule for canceling with inverse cosecant? If we want to cancel something with an inverse cosecant, what we have to have is, where's that? Here it is. Inverse cosecant of cosecant of x equals x if x is in the union negative pi over 2 to 0, union 0 to positive pi over 2, like that, right? If we want to cancel, then x has to be in this union of intervals here, but negative 17 pi over 14 is way outside of that. Okay, so negative 17 pi over 14 is too far to the left on the number line, it's too far negative. It's outside of both these intervals, so no, we cannot cancel, so we have to do what this says to do, which is either cancel or use reference angles. Since we can't cancel, we're going to have to use reference angles. So let's go ahead and do that. Okay, so let's erase all this stuff here, and then we'll start setting this up with reference angles. Now before we move on, I want to point out we could use the fact that cosecant and inverse cosecant are odd functions, but let's not worry about that. It's not going to help us a whole lot. Well, actually it might help a little bit, to be honest, but it's... So you know what, actually, yeah, let's go ahead and do that. So cosecant of negative theta equals negative cosecant of theta. Therefore, cosecant of negative 17 pi over 14 equals negative cosecant of 17 pi over 14. Okay, that's just a property of odd functions. So then up here what we can say is this equals cosecant inverse of negative cosecant of 17 pi over 14. Okay, so that's what we have going on there. Now inverse cosecant is also an odd function. Okay, inverse cosecant is also odd. So therefore inverse cosecant of negative x equals negative inverse cosecant of x. So specifically in this case, inverse cosecant of negative cosecant 17 pi over 14 is negative cosecant inverse of cosecant 17 pi over 14. Okay. Now again, did we have to do that? No, we didn't really have to, but it does help us just a tiny little bit. And I'll explain how it helps us once we get to that step, which is pretty much coming up next. Okay, now, so we got to remember the minus sign out here. And again, this comes from the fact that both cosecant and inverse cosecant are odd functions. Okay, so now we should technically go through that process again, but 17 pi over 14 was also, it is also outside of that special union of intervals here. So remember, if we want to cancel inverse cosecant and cosecant, this number here has to be inside of this union of intervals, but this number is not. It's way outside. Okay. So no, we cannot cancel, so we have to do reference angles, just like we already knew. Okay, just so we have to do reference angles. Okay, so now we're going to find the reference angle for 17 pi over 14. Oh, how terrible. All right. X-axis, y-axis. Okay, so this here is 0, this is pi over 2, this is pi, this is 3 pi over 2, and then 2 pi. Okay, so what we want to do is we want to draw the angle 17 pi over 14. So what we want to do is convert all this stuff to be over 14, then we'll know where it goes. So pi over 2 multiplied by 7 over 7, that's 7 pi over 14. 17 pi over 14 is still larger, so let's keep going. Pi multiplied by 14 over 14, so that's 14 pi over 14. 17 pi over 14 is still larger. 3 pi over 2 multiplied by 7 over 7, that's 21 pi over 14. Well, hey, look what happened. 21 pi over 14 is bigger than 17 pi over 14. So 17 pi over 14 is between 14 pi over 14 and 21 pi over 14. So 17 pi over 14 is somewhere in here. Location is approximate, all that matters is the quadrant. Okay, so this right here is 17 pi over 14. Okay? Okay, great. So now that we have that angle, what did we just find out? We just found out that 17 pi over 14 is in quadrant 3. So what does that tell us about the positivity or negativity of the cosecant? So cosecant of 17 pi over 14 is, let's not say is. So if you're in quadrant 3, cosecant is negative, right? Actually, in quadrant 3, the only thing positive is tangent and cotangent. So in quadrant 3, cosecant is negative, okay? Okay, now what we do is find the reference angle. So now that we found this out, we have to find the reference angle. And actually, this is where the odd properties helped us. So if we didn't use the odd properties, then we would end up drawing negative 17 pi over 14. And negative 17 pi over 14 would be, we start here, go all the way around up here. And then if we did it like that, then before we found the reference angle, we would have to use coterminal angles. So using the odd properties here, using the odd properties of cosecant and inverse cosecant, that saved us from having to use coterminal angles. Not that coterminal angles are that bad, but actually doing this is a little bit simpler than adding 2 pi going around in full circle. Okay, so with 17 pi over 14, we didn't have to do that, which is nice. But with negative 17 pi over 14, we would have had to have done that. Which again, wouldn't have been terrible, but using the odd properties is a little bit easier, so that's nice. Okay, so now let's find the reference angle. So since we're in quadrant 3, the reference angle is alpha, we're going to call it alpha, equals, so in quadrant 3, the reference angle is the angle itself minus pi. Common denominator is going to be 14 pi over 14. So 17 pi over 14 minus 14 pi over 14 is 3 pi over 14. Okay. Okay, so so the reference angle is 3 pi over 14. Okay. So that's what the reference angle is. So remember when we talked about reference angles way back in an earlier video a long time ago, the way reference angles work is if you have an angle theta, or we're doing cosecants, cosecant of theta is plus or minus cosecant of the reference angle alpha, where the plus and minus sign is determined by the quadrant of theta. In this case, theta is 17 pi over 14, and we already know that since theta is in quadrant 3, cosecant is negative, so we're going to take the negative. Okay, so in other words, cosecant of our given angle equals negative cosecant of the reference angle. That's how reference angles work, so remember that. So then what we have in this specific case is cosecant of 17 pi over 14 equals negative cosecant of 3 pi over 14. Okay, so that's what we just found out here. Cosecant of 17 pi over 14 is negative cosecant of 3 pi over 14. And again, the reason is that 3 pi over 14 is the reference angle for 17 pi over 14, and we have the minus sign because cosecant of 17 pi over 14 is negative. And the reason it's negative is because 17 pi over 14 is in quadrant 3, and in quadrant 3, cosecant is negative. So therefore we have this, okay? Okay, now we just plug it back in. So coming back up to here, this is negative cosecant inverse of what? We just found out that cosecant of 17 pi over 14 exactly equals negative cosecant of 3 pi over 14. Okay. Well, hey, so what do we have now? Right now we have negative inverse cosecant of negative cosecant of 3 pi over 14. So let's again use the fact that inverse cosecant is odd. Okay, so we still have this minus sign out here. Then we're going to pull this minus sign out. Well, okay, sorry, we're not really pulling a minus sign out. But if we use the fact that inverse cosecant is odd, then what we could do is write it like this. Okay, so again, well, let's put an equal sign in there. Okay, so then this equals, this minus sign comes from this minus sign. Okay, this minus sign is this minus sign, which comes from that minus sign, which came from that minus sign, which came from that minus sign, okay? And then this minus sign right here comes from this minus sign. And again, this minus sign now appears on the outside of inverse cosecant because inverse cosecant is an odd function. Okay, we already used that fact earlier in the video. Now, negative negative becomes a positive, so this is just cosecant inverse of cosecant of 3 pi over 14. Oh, and check that out, that's great. Now, 3 pi over 14 is between 0 and pi over 2. Okay, that's great. So what's so significant about that? Well, now that means that we can cancel, right? Because remember, inverse cosecant of cosecant of x equals x if x is in this union of intervals here, negative pi over 2 to 0, union 0 to pi over 2. Okay, actually I guess the way I wanted to write that is this. Okay, that doesn't actually matter, it's true either way and it's good enough. So inverse cosecant to cosecant of x is x if x is in this union of intervals here, and as it turns out in our case x is 3 pi over 14. Okay, so 3 pi over 14 is inside of this interval here, so we're good. That means we can cancel, and then our answer is just 3 pi over 14. Okay, so isn't Trig amazing? All this crazy stuff we can do to evaluate something that looks so goofy. But anyway, that's example 12 of trig with inverse trig. So what do? We followed this flowchart, and we eventually got to the point where we had to use the complementary angle theorem. Again, we can use that not just for acute angles, but for really angles in general, as long as we're not violating a domain restriction. Okay, so then after that we had to either cancel or use reference angles, and in this case we had to use reference angles, and that's exactly what we did, and we ended up with 3 pi over 14 for our final answer. Okay? So that's example 12 of trig with inverse trig, a couple more examples coming up.